Ward here. This is video 4 of 4 in our pipe potpourri lecture. Just one last example. Oftentimes we're given that minor loss coefficient KL, but here's an example where you might have dreamed up an experiment to determine what is KL for a filter. So the setup here is that we've got a 10 centimeter diameter pipe. We've got air flowing through that pipe from left to right. And in this gray color, what I'm trying to denote for you is that we've got a filter that's put in line. So an application here might be something like the air filter that's in a forced air furnace, which you should be changing out approximately quarterly. And you've also got a manometer in this problem, which indicates to us, one, we have to still remember hydrostatics, and two, we're going to have to deal with that manometer, and because the water level is changing in the manometer, that is an indicator to us that there is a pressure drop through the problem. So the setup here gives us some information about flow rates. It gives us a pressure at point 1, a temperature, and asks us to determine the minor loss coefficient KL. So there's two pieces to this problem. The first that we're going to tackle is the manometer problem. And so you'll recall our strategy for manometers is where we end up, point 2, is equal to where we start at point 1, and then we account for changes along the way as we move through the fluids. So as we move down through the air, pressure would increase by an amount equivalent to the specific weight of air times h1, whatever height we dropped. You could move horizontally across the column. You move up through 4 centimeters of water. Moving up means pressure is going down, so minus gamma for water times 4 centimeters, and then minus gamma air times whatever that height 2 is in the problem. So that's our standard manometer equation. Now in this problem, we are not given dimensions H1 and H2 as I've labeled them in red. And so to proceed here, I'm going to assume that those contributions to pressure are negligible. The specific weight of air is incredibly small, and given the scale of this problem, those might only be a few centimeters anyhow, so we're going to neglect those two terms. So reorganizing it, that pressure drop P2 to P1 must be equal to the height difference in that column of water. So specific weight of water times 4 centimeters, or a total of 392 pascals. So the pressure difference, or the pressure drop from point 1 to point 2 is 392 pascals. Right? And so we know why that pressure drop is happening. That pressure drop's occurring because we put in the filter. Right? There's a loss of energy moving through the filter. It's removing energy in the form of pressure head, and so we get a reduction in pressure. So now we can pursue the energy equation part of this problem. And so now I'm writing out my energy equation from point 1 to point 2. So on the left-hand side at point 2, we've got energy in pressure, elevation, and velocity forms. On the right-hand side, we have point 1, pressure, elevation, and velocity forms. And we've got that minus KL times V squared over 2G. Right? And that's to account for the minor losses. So this problem simplifies for us a bit. Points 1 and 2 are at the same elevation, and the pipe diameter hasn't changed. So we're going to assume that V1 is equal to V2. So a little bit of bookkeeping here, and we can get ourselves to the pressure drop over the specific weight of air is equal to the minus the minor loss coefficient KL times V squared over 2G. And just to be clear, let's make sure we're noting that's the specific weight of air, because we're moving from point 1 to point 2 through that fluid that's flowing through the pipe and through the filter. That's through air. All right. Now, we didn't have a velocity in this problem, but we can calculate one. And so you'll see here, what I've done is remember that velocity is equal to discharge divided by area, and I can square all of those. So I've taken a V squared away, and I've replaced it with Q squared on the top and area squared on the bottom. And I'll go ahead and plug in some things that I know. Pressure drop we calculated in the manometer problem of 392 pascals. I looked up a specific weight of air at the pressure or temperature given of about 14 newtons per cubic meter. On the right hand side, minus KL, we don't know. And this was a pressure drop, so you'll see on purple here, I'm just going to remind you that should be minus 392 because the pressure at 2 is lower than the pressure at 1. It was a drop of 392. And then on the right hand side, minus KL, which we still don't know. On the top, I've got Q squared, so 7 cubic meters per minute we were given. And you see I've got a unit conversion in there in the numerator from minutes in the denominator to seconds in the denominator up there for Q. And then in the denominator on the right hand side, 2 times gravity, 9.81 meters per second squared, times area, which is pi over 4 times the diameter of the pipe squared, so 0.1 meters squared, and then that whole quantity squared, because we had an a squared in the denominator. Oh, all right. Tricky things in this problem is that Q equals AV conversion that I showed in orange to help you get to that unknown velocity. You have to have a manometer problem, and you've got to keep track of your units pretty carefully here. And when that's all said and done, I get a minor loss coefficient of about 2.5 for that filter, which is what we were after. All right, folks, I hope this was helpful to you, and I will see you back in the classroom. Have a great day.